So, should we start now? Okay. So, what I will do now, we will just go for first 10 minutes to refresh what we have discussed last time. Then a couple of things which Professor Amal told me to cover. So, I will just cover only 5 minutes, linear quadratic regulators. Then we will go to the next topic. Is it okay? So, what I discussed yesterday is that which I want that all our academic staff should tell to the students that nothing exists, it starts. Because unless you know that thing, your understanding of the poles, zeros and system concept will not be clear at all. So, everything is energy and we all are vibrating at different frequencies, right? That is clear, that must be very clear. That we are all vibrating bundles of energy at different frequencies. And we have got several characteristic modes. We vibrate at different frequencies having many characteristic modes. And those are the poles of the system or the eigenvalues of the system. And they are also called the singularities of the system. They are system singularities. And second point is, we have also got some zeros. That is the frequency which will not respond. Okay, we will block that frequency. As I gave you some analogy, that you are not supposed to answer all questions. Certain questions you will not answer. So that is the zeros of the system. Then we talk about static systems, dynamic systems. Dynamic systems has got at least one energy storing element. Because of the memory, there is a possibility of instability, right? That's the. Next, we say that there is no need of designing any controller. If the open loop performance is satisfactory, that's fine. There is no need. We are happy with that. But usually the open loop system is not satisfactory. So we have to design the controller. But we have to design the controller provided the system is controllable. If the system is not controllable, there is no point that we should design the controller. That point I discussed. But what is not emphasized in the textbook is controllability, that particular property of that is not the property of the system itself. This is the property of the system matrix as well as the input matrix. That means, as I told you, the same system can be controlled by changing the input signal, right? B matrix. That is very important. So, if the system is not controllable, you have to make it controllable if possible. And if you cannot make it, don't waste your time. That is just mere waste of time because the system will not respond, right? There is an important theorem, the pole placement theorem, that says if the system is controllable, condition number 1, then it is possible to place the eigenvalues anywhere in the S-plane by an unconstrained control signal and using state feedback. So, there are 3 conditions now. The system must be controllable. The feedback mechanism is not output feedback mechanism, it is a state feedback. Output feedback may not possible place the poles anywhere. So, first the system must be controllable. You must use not output feedback but state feedback. And you should not constrain the control input. Control input should be unconstrained, right? With constrained control input, you cannot place anywhere in the S-plane, right? But there is a catch. The catch is, we assume that because you are using the states as the feedback, we assume that the states are measurable. Or you can access the states, right? If we cannot access the states, then you have to estimate it. We will talk about the estimation today in a different topic. We have to estimate it. How to estimate it? We have to estimate it by using a formula from the output measurements and using an algorithm with a formula that is called the observer. Observer is essentially a mathematical expression. So by using the observer, you can estimate the states, and instead of the actual states, you put the estimated state. I am just writing here. U is equal to minus kx earlier. Now this u will be equal to minus k x cap. So this x is now replaced by x cap, and this x cap is obtained from an observer. Now the point is differential. Observer can estimate the states if the data is not corrupted by noise. That point is not emphasized here. If the data is not corrupted by noise, then we can estimate the state of the system from output measurements by an observer. But if the data is corrupted by noise, you can estimate the state not by an observer but by a Kalman filter. Kalman filter does the same thing. It estimates the states. Kalman filter is essentially estimator, right? But if noise is there, then you have to use a Kalman filter. So what is the difference between the Kalman filter and observer? They both estimate the states. One works when the noise is not there, another will work when noise is there, right? Now say this, and that particular estimator, it has got a name that is called a linear quadratic estimator, Kalman filter. Linear quadratic estimator, LQE. In the MATLAB, there is a command called LQE. This command will estimate the states. You give the noise statistics. Okay? You give the noise statistics. LQE, linear quadratic estimator, essentially a Kalman filter. Okay? So it will estimate the states. Now you can ask him, why not an observer? Observer is fine. If there is noise, observer will not work. Kalman filter also will not work. You see, it is linear quadratic estimator. It is linear, it is quadratic, and it is an estimator. What is the linear? What we are talking LQE, it is only applicable for linear systems. Kalman filter can be designed for nonlinear system, that is a different issue. But linear quadratic regulator is only for linear systems. It assumes the performance index is quadratic and is an estimator. So therefore linear quadratic estimator. Now comes noise, because when there is noise, we have to estimate the states by using estimator, Kalman filter. Noise is the problematic things. We will talk about these things today itself in the other aspect. I will just give an example here. See here, a plus b whole square. Let us see. Very fundamental. A square plus 2ab plus b square. Everybody knows it, right? This is an identity, this is not an equation. Okay, this is an algebraic identity, this is not an equation. Okay. How can you compute a plus b whole square? You see, this is a very simple thing, but it gives you a very clear message. Just wait for now. A plus b whole square, you can compute provided you know precisely what is the value of A. You know precisely what is the value of B. Then only you can calculate A plus b whole square, right? That means if A is a deterministic variable, B is a deterministic variable, then only you can find out A plus B whole square. If A is a random variable and B is a random variable, even A plus B whole square you cannot do it. Suppose I will say you the temperature of this particular room is a random variable. The temperature of the next room is also a random variable. You cannot do the addition of the temperature of this room and the temperature of that room. You cannot add it because you don't know its value precisely. Because you don't know its value precisely. You understand this point? A random variable by definition whose value is not precisely known. And if you do not know the value, how can you compute? You got a point? So, with tricky things. So, what we will do, if the variable is a stochastic variable, a random variable, you convert the random variable to a deterministic variable. Not a merely a deterministic variable, but I am telling from that understanding concept. Convert it to a deterministic. Then you apply the deterministic formula. Because this formula is for deterministic variables, right? Now what is that? The temperature of this particular room is a random variable. Because you do not know what is its value precisely, right? But over the day, if you measure the temperature at each time and find out the mean value of the temperature of this room is a deterministic variable. You got my point? The temperature is random, but if you take the mean, it is not random, it becomes deterministic. So now you can A plus B whole square instead of A plus B whole square, you see, you can instead of T1 plus T2 temperature whole square, you cannot compute. I am writing like this, you cannot compute, but T1 bar plus T2 bar whole square you can compute. Because T1 is a random variable, T2 is a random variable, but T1 bar and T2 bar is not a random variable, they are deterministic. Right? So we are applying mean value of the probability operator, or any type of many sorts of operators are there. So that converts this stochastic variable to deterministic phenomena, right? So linear quadratic estimator, it will estimate the states when the data is corrupted by noise, and noise should have the Gaussian statistics. Noise can vary, you see the statistics should vary in the Gaussian pattern, non-Gaussian pattern, there are different types of probabilities there, okay? So if you are estimating the states using the Kalman filter, okay, then another thing I will tell you, linear quadratic estimator. In engineering and science, we have got mainly two problems. One problem is called the regulation problem, another is called the tracking problem. Regulation problem means we want, say for example, the power system. We want, no matter how the disturbance is there in the system, the frequency deviation should be 0. That is, the frequency should be maintained at 50 cycles. The deviation in frequency should be 0. This is a regulation problem. The frequency should be regulated to 0 under disturbance. Clear? This is a regulation problem. What is the tracking problem? Tracking problem is different. The speed of the DC motor should be this 1500 minus 1500 plus 1500 like this. You got my point? Tracking problem, you see here. See, this speed, right? Tracking problem, or else tracking problem, radar tracking problem, it is tracking, right? Robot path planning is a tracking problem, it is not a regulation problem. You track it, right? You track it. In the pole placement type controller which I discussed yesterday, it is a very powerful controller because you can place the poles anywhere in the S-plane by unconstrained control signal, right? But the problem is where to place the poles, where to place the poles, right? So to avoid that, a new theory came up, linear quadratic regulator. Instead of placing the poles, you optimize one performance index. You optimize one performance index, usually the performance index is like this. You optimize a performance index, okay, X transpose QX plus U transpose RU, okay, and find out the same control law, U is equal to minus KX. So this problem is called a linear quadratic regulator. The name is, this is applicable for linear system. The performance index which you are minimizing is a quadratic performance index, and you are solving a regulation problem, right? Not a tracking problem, not a tracking problem. So therefore, this is a linear quadratic regulator. It is essentially a state feedback controller. And in the MATLAB you will find LQR. You give a command like LQR, it will give you the K. K is equal to LQR, and there is something, you see. All the matrices you can give it, you can get it. But in pole placement you give K is equal to place or occur, ABP. You see, same K, but you will get different value of K, but this is the K, the state feedback again, LQR and place, linear quadratic regulator. So linear quadratic regulator essentially is a regulator, and it optimizes a quadratic performance index and is applicable to linear systems. Therefore name, right? Now same thing, state feedback. If the states are not measurable, you have to put an estimator. Linear quadratic regulator can also be used with an observer, no problem. But usually data is corrupted by noise, so you have to estimate by a linear quadratic estimator, right? So linear quadratic regulator plus the estimator LQE is give you linear quadratic Gaussian controller. We say observer based controller. Observer will estimate the state feedback combined together, observer based controller. Exactly same thing, linear quadratic regulator. It is not placing the poles. What it does? It optimizes the performance index. Linear quadratic estimator, it estimates the states, combine them together. It is linear quadratic Gaussian controller, right? Why Gaussian? Because we assume that the noise follows a Gaussian distribution. Okay? And why linear? Because it is applicable to linear system. And quadratic because the performance index is quadratic. Got my point? So linear quadratic regulator plus linear quadratic estimator is equal to linear quadratic Gaussian. Now, if you want that it should track something, you have to put an integrator. Yesterday I told you the integrator can do all these things, steady state. Those things are always there. Okay, but this is point. So, I will close these things now. Now we will go to the next one. This is lecture 3, na? Modeling. Bigger? Full screen mode. Is it there or not? No? Earlier it was full screen. Is it there? No? Huh? Start. Oh dear. You are intelligent. People in the area of all engineering and science, they always say, we are genius, we are intelligent, we can do everything. But only the thing you do one thing, you give us a model. Given the model, they can do everything. Everyone, you see, 99% people, more than that, given the model, they can analyze the system, they can design controllers, they can do all sort of things, right? But who will give you the model? Who will give you the model? If you give model is given, that's fine, easy, right? So the question is, we will discuss all this in detail, and today also in the tutorial you will do it by yourself, and that will be easy, not like yesterday's things which you could not do it, you will do it. People will say, give us a model. Give us a model, then we'll do it. The problem is, if I want to go to the market to purchase the vegetables from a house or from the, I'm living in the campus and there's a vegetable shop outside, if I want to go to there, a simple bicycle will do the job, right? Simple bicycle will do the job. If I want to go to the beach to have a view, I can take my car. If I want to go to Bombay, I need either a train or plane, right? And if you want to go to super space, then you require something different, right? So the question is, in your house, everything is there. You have got a bike, you have got a bicycle, you have got a car, okay, you have got money to buy the plane tickets also. The question is, which one you will take? So taking a plane to go to the vegetable shop is not foolishness, it's a bloody foolishness. You got a point? You may think it is easier to know. I'm telling you, this is the most difficult part. I've got a student, I remember he was a mechanical engineer and he did a PhD. I was the co-supervisor, Oliver Grant. One day Oliver came to me and said, Dr. Swain, I will work on chaotic systems. We'll discuss those things later on in the nonlinear system. I told Oliver, your problem is designing controller for the helicopters and all these things. You start from the LQR, LQG and then proceed further. No. Can I identify, he told, can I identify a helicopter model? I told, why you want to identify a helicopter model? Why? No, I do not know, because I knew that you have worked with a very big source. From the Google Scholar I found out, so I thought, let us do some modeling. I told, you see, you must first decide what you are going to do, why you want to do it. Because doing is not a fun. It requires lots of mathematical knowledge, and so many other things. We will see that. So taking it, whether you will take a bicycle, plane, or a bus or a train, that decision is extremely difficult. As you have lecture procedure, you will know it, right? So similarly, fitting models, how to fit the models, we will discuss later today. But which type of models? Models are many. There are so many types of models. Let's see. Modeling is given a set of input of data, find a mathematical model. Okay, see. First, let me go to this slide, and then we'll see. In the modeling, what you do, I will come back to that point. I have got a system, and I have to fit a model. So I will apply the same input to the system, same input to the model. So I will get an error, then I will use this error to update the model, right? Very standard system identification, right? Things are not that easy. And I am telling you in this lecture and coming lectures, I will tell certain controversial things, okay, which many people think that is wrong, and we think that is right, 100% right. And we have got the authority to tell that thing, because we have published papers on that, and we have worked in the big source in the world. We will say, and the people have to follow. There is no other way out. We'll see that, right? This diagram looks very simple. I want to mimic the system behavior. The model has to mimic the system behavior. You apply the same input to the model system, same input to the model, you get the error and update the model. This is the standard thing. Which model? Models are many. Let us see. Let me give an example. You see, I am here. I have got many models. See, first model. I am the son of my father. One model. Second model. I am the father of my son. Clear? Third model. I am the teacher of my student. Fourth model. Otherwise, right? So many different types of models. Which model you should use? Extremely difficult decision. Which model you will use? Which model you will use? Right? There is a saying, a person with one watch is sure what time it is. A person with multiple watches is never sure. Because no watch will give the same time. There will be at least some precision wise, there is some error, right? If there is, see, you will find, if you are getting one job, then you go and join. In a campus, if a student is intelligent, he gets multiple places offer. One from Google, another from Microsoft, another is from Accenture. Then he is problematic. Which one he will take? If you have got a point? So models are many. Which model you will use? Various types of models you see here. There are many types of models. Parametric models, non-parametric, continuous, discrete, long, distributed, deterministic, stochastic, linear. Oh dear. See, too many choices. Man with one watch is sure what time it is. Man with multiple choices is not sure. Right? Which type of model to be fitted to the data? Which factors will determine that which model to fit? That is a difficult decision. Okay? Yeah, difficult decision. Okay. There are different types of models we'll discuss today, and we'll also see the and second thing is, why you are going to fit the model? As I told you yesterday, it is not an intellectual form, it is not an intellectual gymnastics. Because Ministry of Energy, Ministry of Human Resources is giving some money, and there is a GAN course is conducted by two professors from your own department, and a person coming, idiot fellow coming from outside, Government of India is giving money. It's not a bloody form. What a point? That was to goal. Why you are doing it? As the student told, Dr. Swami, I want to fit a model. Why the hell you will fit a model? No, I don't know. You don't know why to fit the model. Then go away. What about? Models, whether you will use it for prediction purpose, we will discuss those things, prediction problem, control problem. Whether you will use it for control purpose, whether you will use it for analysis purpose or verification. What is the purpose? First you decide. Why I am telling these things? Because you are academics. Whenever some students come here, I am telling you one thing. I have got around 25, 30 students, PhD students I have supervised. Problem is not by solving the problem. People are intelligent, they can solve the problem. The problem is finding the problem, formulating the problem. That is important, not the solution. Solution is easy. A man in the street I can bring him from the Queen Street, he can solve the problem. I tell to students, I can go and stand in the Queen Street, ask the people, come and solve it. They will come. Got a point? Problem. Okay. So you must be very careful about that. Extremely important thing. I will discuss these things later on because I have given an example here. One day one of my friends, we are colleagues in the Aris Raulkala. He is now UNSW, Australia. So he came for a PhD examination and he was talking that we have got a manufacturing problem. Okay, I am not discussing those things. So they have got a fiber, they have to manufacture. So there are 20, 30 variables, input variables, and there are output variables. So they do not know how these input variables affects the output variables. So we are discussing on the launch table. I told you, see, what you are talking about, he is a mechanical engineer. It is not a control problem. It is a prediction problem. It is not a control problem. It is a prediction problem. So the prediction problem, and there is no need of any interpretation also. So a neural network can do the job. Neural network is very good for prediction. Neural network is very good for prediction. Completely useless. Completely useless for interpretation. You cannot interpret anything from the weights of the neural network. Okay? I told this is the prediction problem, and neural network can do very good for prediction. Give it. And I have got a student from Sri Lanka. He is now in the German aerospace in Chatura. I told Chatura, you do it, and Chatura did it. And we published a couple of papers in the transactions. So we have to identify what is the prediction problem, which type of problem it is, right? So model building begins with an objective. Assumption. You see, all these wordings I am telling you are very careful. Precisely, model building begins with an objective, with an assumption, and a priori information. And second line is, be aware of the assumptions and beware of the assumptions. You must be aware that what assumptions you have taken, and you must be very careful what assumptions you have taken. Okay? Suppose you are assuming the noise is Gaussian, but actual noise is not Gaussian. It is something different. So you will not get the result. Got a point? So you must be aware of the assumptions and also be very careful about the assumptions. So first thing, why you are fitting a model, not a phone. Which type of model you will fit it, right? There are many types of models. That also you have to decide. And once those things are there, other things become straightforward. In this particular course, because we are going to study minimum variance controller and subsequent adaptive controller, if you want to design a minimum variance controller, we will discuss those things, not today, tomorrow or something like that. If you want to, I am telling you, if you want to design a state feedback controller, the system must be modeled by a state space model. If you want to design one H infinity or robust controller, system must be in state space. If you want to design a generalized predictive controller, system must be a discrete parametric model, which we are talking about. Okay. If you want to design a feedback linearizing controller for nonlinear system, system should be in a different format. First you get a model in that particular format and do it. You got a point? I'm just giving an analogy here. The same person is same. I want that he should act as a king. So which type of robes he should wear? Should he wear this type of shirt with the half sleeves? The king will have nice dress, velvet dress, right? The same person will act as a beggar. Should you give him a velvet dress? You have to give a different dress. Got a point? So similar thing. The system may be same. What do you want to do with the model? Accordingly, you will get it. Got a point? So that is a very crucial point. If a person is doing the beggar role in the drama and you put a velvet dress and with a head, crown, how it will look? It will look bad, right? Remember, I can talk many things, but I don't want to divert. You see, because my father-in-law is a professor in the literature, so I read quite a lot of literature. I read a lot. I'm a voracious reader. A drama is good. A theater is good. When you go to see a movie, okay, movie there are around thousands of people are watching, or here in India, lakhs of people are watching, okay? Everybody is saying the movie is good. The movie has got 50 characters. Somebody will say, that heroine, she is so beautiful and glamorous. Then others say, forget about that heroine, she is bloody useless. Have you seen the acting of Amir Khan? He nice. Then another fellow will tell, what does the hero is doing? See the villain, ominously is villain, so villainous dialogue you can see. Then somebody will say, all is nonsense. See the comedian, Johnny Lever, how he is acting. Now see, the picture is successful. You see, the audience is different characteristic. One is liking the hero, another is liking the heroine, another is liking the villain, another is liking these things, right? A picture is successful not because the hero is acting well, or the heroine is glamorous, or the villain is doing his duty properly. It is because everyone is doing their duty properly as intended by the director. Got my point? What the director intends, if the comedian will not do the comedy, the entire show will flop. Got my point? So this is what exactly these things. When you are doing certain things, you are designing a minimum variance controller and using a state space model, it will not work. It will not, just like putting a very nice robe and doing the job of a beggar. It will not work. Got my point? So you must be very careful. We will discuss today this particular hour parametric models, because we will use this model for my design. Okay? Discrete parametric model. It is discrete domain and parametric models. The structure of this thing, I am just going very quickly, we can go. You see here, the main difference here is, it has got a noise model and it has got a process model. The system, the data is corrupted by noise, you are measuring the data and the data is corrupted by noise, right? So you want to fit it, right? So this model, what happens? There is a noise model and there is a process model, right? What a noise model will do, not exactly true, it will capture the noise dynamics. Now noise doesn't have any dynamics, but I am telling in the sense, it will capture the noise part and the process model will capture the dynamics of the system. Say, I am giving the analogy here. In the classroom, not only the academic staff, there are some bloody idiots coming from outside as well. Right? So what I will do now, I have my own mechanism, I am fitting the model. I will catch the way the academic staff will be separated and those people who are useless, they will be separated by a, right? Because my people are there, they can easily detect who are the useless people. That's the mechanism. So the system has got two models. One, the process part and the noise part. The process part will capture the system physics. Noise part will do these things. Standard model.
ABCDs are not same level.
Yeah?
ABCD, whatever the notation we are using,
Yeah.
they are different than the state space.
Yeah. That is different than state space. That's very important. This is not a state space model. This is a parametric model, just like a transfer function model. It is not. Remember, yes, the Professor Amalkar has told rightly. Remember, this is not a state space model. This is a discrete parametric model. Okay, this is the structure. Because I usually use it for a minimum variance controller. Okay, minimum variance controller we cannot use state space model. MPC we can use it, but not. Right. The structure of the model here is, you see now first thing here, the usual structure is this D polynomial here, the noise polynomial, the denominator is D, the process denominator is A. Right? Just check it here. So that is the whole difference we will make later on. Just a minute. And another thing is, the A polynomial structure, first one is A1, and this is called the monic polynomial. They are called the monic polynomial. Don't enter into so many mathematical terms. And B polynomial in its first term is not 1. First term is B0. Remember, those points are important. Those points are important. You see the definition wise, this is by definition. A polynomial, C polynomial, or D polynomial, the first term is 1, 1, 1. B polynomial, the first is not 1. It is some constant, B0. Okay? This is the structure. This is the structure. We'll talk about those things, structures shortly. Just don't refer that. Now, there are different types of models. One model is autoregressive model. Autoregressive model, that's a general structure, but not necessarily. There is one model is called autoregressive model. I will explain only these three terms now carefully. Autoregressive model, yk is equal to 1 by a j minus 1 ek, or yk is equal to, see the point here, yk is equal to minus a1 yk minus 1, yk minus 2, yk minus na. The present value of y is a function of the past values. Clear? This point, present value of y, yk is equal to a function of yk minus 1, yk minus 2, yk minus 3. Right? So, regression. Have you heard about the term regression in statistics? Regression, you see, okay, again we have to go to that. Without Indian spirituality, your understanding of engineering knowledge would be a big zero. I don't know whether it is appropriate to tell here because it is getting recorded, but doesn't matter, this is the truth. The entire creation was started. How many of you are doing some meditation? Anybody is doing some meditation? Complete silent. When I say silent means silent. No thought. When I say no thought, no thought. No thought. If you don't have any thought, you yourself, even today also you can find it, you will hear a particular sound. That sound is the vibration of the Hiranyagarbha, is the vibration of the universe, cosmos, Omkar. You will yourself will listen. I am telling you, this is a fact. This is the fact I am telling you. You will listen it. Every day you will listen it. But you have to be completely silent, fully silent. When in silence, no thought, you regress and regress and regress and regress. You go back. Regress means past. Progress means future. Regress and regress and regress. So in the Sanskrit we have got Onkara Bindu Sangyuktang Nityang Dhayanti Yogina. That's the correct thing. See, if you regress it, you will find that particular sound where the entire creation has come out. What I point? Regression. You will find, I don't know in Indian television it shows or not. When I was in England, in British Channel 4, there is a program comes hypnotism. There is a person who will come and he will bring a particular person, a live show. He will ask him to sleep and he will say, okay, where are you? Where are you? Where are you? He will say, I am in Ireland, Dublin. Go back, where are you? He will be telling that. He told, yes, I could see a church. There is a tree, no leaves, it's winter. It's snowing now. I'm feeling, he will tell, regress. You see, regression. If you regress, go, hypnotism, people do it. So they go it and they find out what is there, right? Similarly, this is the regression. Yk is a regression. Yk minus 1, yk minus 2, yk minus 3, yk minus 4, yk minus infinity. If you go to that source, you will find out. It's an auto-regression. Because you are finding yk, it is the regression of itself, auto-regression. So this is an auto-regressive model, extensively used in speech processing. In the speech processing, this type of model is used. Okay? Auto-regressive model where the output is described by its own regression. Clear? Output is described by its own regression and EK is the modeling error. This is one type of model. Second type of model is a moving average model. You see the structure? Where the output is not a regression. It is a regression not of itself. It is a regression of some noise sequence. Ek minus 1, Ek minus 2, Ek minus 3, moving average. That is moving average of the noise. Okay? It's average, moving average, because Ek minus 1, K minus 2, K minus 3, you are moving in the regression pattern. Then auto-regressive moving average model, you have got an auto-regressive part and you have got a moving average part. ARMA model. So auto-regressive model, moving average model, ARMA model. Another model, different types of models. ARX model. This model is important. ARX model, here you see, this is the standard transfer function model. Be careful here. You see the generalized structure of noise model, C by D. If you see the diagram here, just compare here. This model is diagram here, C by D. The noise model is C by D, but in ARX model, you see the C by D, the C by D is 1 by A. See the point? This is 1 by A. This A and this A, that's same. See the difference, okay? C 1 by A. And this model is the standard transfer function model. Yk is Yk minus 1, auto-regressive part, plus the input part. This is output and this is input. But it is called ARX model. ARX model, you will do today in the tutorial, very simple one-line command. ARX, that AX term is coming from statistics, extra input, exogenous input, auto-regressive with the extra input. ARX model, if you see the structure, you will find this A is there, not a D. Another model is ARMAX model. Rmax model, here you see that C term is there, but this A term and A term, they're same. Process model or Rmax model. So mainly, see this point I am telling because I will not next lecture, but subsequent, maybe tomorrow, the output of the system is described by a discrete parametric model. Z to the power minus D, D is the some constant, you see, delay, B by A, UK, just like transfer function, plus C by A, EK, it has got two parts, process part and noise part, right? This is the model. This model we will use it in designing the adaptive controller, okay. And another important point, remember, the denominator of the process model and the denominator of the noise model, they are same. Another point, very important. This A here and this A, they are same. They are not different. Okay, Rmax model. This model will be used to design the adaptive control, which I will discuss tomorrow. But today we have got so many things to discuss, okay? So this is for all these models which I discussed can be described by this form. How it is described, I will explain you now. Say yk is equal to z to the power minus 1 b0 plus b1 z to the power minus 1 by 1 plus a1 z to the power minus 1 plus a2 z to the power minus 2. So this one will be represented as yk is equal to minus a1 yk minus 1 minus a2 yk minus 2 plus b0 uk minus 1 plus b1 uk minus 2. Okay? This model can be represented in a general structure. What is the structure? This point we will start from the next lecture because this is, I will explain these things. Yk is equal to theta 1 p1 k. You see, this k is not equal to, that means a function of k only. Theta 2 p2 k plus theta 3 p3 k plus theta 4 p4 k. If this model is represented like this, that means p1k is equal to yk minus 1, p2k is equal to yk minus 2. I'm just writing this, theta 1 is equal to minus a1, theta 2 is equal to minus a2. Do you understand these things? The same system, this point, please keep in mind, this model can be represented in the form yk is equal to theta 1 p1, theta 2 p2, theta 3 p3. Where you see, if I just map it, this p1k is equal to yk minus 1, p2k is equal to yk minus 2, p3k is equal to uk minus 1, and p4k is equal to uk minus 2. Clear? So all these models which we discussed, this model has got a speciality. They are linear in parameters. They are linear in parameters. Let us discuss a little bit more on this. Linear in parameters. You see, here, example I have given. Yk. Professor Bilakam, just remember that we are going to put that objective questions for the people. It comes to my mind that we will put this type of questions. Yk is equal to theta 1 yk minus 1 plus theta 2 uk minus 1. Okay? 5, 6 examples I'm taking now. This is a linear system or nonlinear system? This model. Linear or nonlinear? Linear. Theta 1, you understand the parameter and signals. Force is equal to mass into acceleration. Force is a signal, acceleration is a signal, mass is the parameter. Voltage is equal to resistance into current. Voltage is a signal, current is a signal, resistance is a parameter. So yk is equal to theta 1 yk minus 1 plus theta 2 uk minus 1. Yk minus 1 is a signal, uk minus 1 is a signal, theta 1 and theta 2, they are the parameters, right? So here, this system is linear and nonlinear. This is linear, right? This is linear, okay. Just I am writing here. This is linear. Is it linear in parameters or nonlinear in parameters? Theta 1 is linear, theta 2 is also linear in parameters. LIP I am writing here, in short, linear parameters. Second example is here. Yk is equal to theta 1 yk minus 1 plus theta 1 theta 2 yk minus 2 plus theta 3 uk minus 1 plus theta 3 into theta 4 uk minus 2. Linear system or nonlinear system? Linear. System is linear. Yk minus 1, uk minus 1, uk minus 2. System is linear, right? Linear in parameter or nonlinear in parameter? Nonlinear in parameter because theta 1 is multiplied with theta 2, right? Theta 3 is multiplied with theta 4, right? So it is nonlinear in parameter. Clear? Third example. Yk is equal to theta 1 yk minus 1 plus theta 2 y square k minus 2 plus theta 3 uk minus 1 into yk minus 1. This system, linear system or nonlinear system? Huh? Nonlinear. Linear in parameters or nonlinear parameters? Linear in parameters. Got a point? This is a nonlinear system, but linear in parameter. And subsequently other things will come up, right? If the model is represented as a linear in parameters models, if it is linear in parameters, then we can use least squares techniques to estimate the parameters. Clear? This is the point. Neural network, the so-called multilayer perceptron MLP network, which we have studied in 1990s, okay? It is not linear in parameters. MLP network is not linear in parameters. Radial basis function is a linear in parameters models. RBF network, neural network is a linear in parameters. MLP network is not linear in parameters. So we cannot use the estimate the parameters using the linear least squares technique. We have to use the back propagation or other different Gauss-Newton method, Levenberg methods, all these other methods are there. Okay. So if, understand this point here, if the system is represented in a model which is linear in parameters, then all the least square based methods can be applied to estimate the parameters. Clear? If it is not linear in parameters, then you are in trouble. Right? So that is why we say we ask the question people, why least square technique is not being used here? Why back propagation? Fundamentally there. You have to understand the fundamentally because there is not linear in parameters. Radial basis function network, RBF network, is linear in parameters. So you can use the standard least squares techniques. Okay. Similarly, just under 5 minutes. Yes, yes, y is equal to theta 1 plus w1 plus 5 minus the center and all these things, radial function. Okay. Volterra series. This is for linear system. If you want to represent the system in nonlinear systems, there are so many different ways. One is the standard Volterra series. So Volterra series is an extension of the standard linear impulse response function. H1 tau ut minus tau linear system. Then you use higher order kernels. I am not telling that you should know these things. It is a bit complex. Volterra series, but it is linear in parameters. It is linear in parameters. Volterra series is being extensively used for nonlinear system identification. Okay, Volterra series. And there are many other types of system models which are used for representing nonlinear systems. Hammerstein model, Wiener model, sandwich model. Okay, but I want to tell you one thing here. This modeling thing, very few groups in the entire world working on this. Very few groups, okay? Just countable numbers. One group in University of Sheffield where we are working Steve Billings and his group, and subsequently we bifurcated to many places, some people. Hammerstein model and Wiener model is being extensively used in biomedical signal processing. This is being used by very few people. When I was in Canada, I was visiting a person called David Ostick. David Ostick uses it. If you say this Hammerstein Wiener model, people say, go to David Ostick. He will tell. Nobody else. I mean, when I say nobody else is using actually. Hardly you just count how many people are working on this. Okay. Kalman filter, Kalman filter, if you have got a data and you want to filter it, then you have Kalman filter. But the question is, I'll tell you where the modeling comes. Give me a practical example. We have got some data for the renal blood flow in biomedical data. We got it from the Department of Physiology, from the medical school. We wanted to fit a prediction model. So one fellow, one of my students, he is a master student, he told Dr. Swai, why don't we use a neural network? Then that other person is a doctor. He just laughed in the meeting. He told, what the hell I will do with the neural network? He said, what the hell is not a bad term in foreign countries, very common term. So what the hell I will do with the neural network? Neural network can predict. But I want to know how, suppose a patient is sitting on the operation bed, something is happening, I will see that which parameter of the model I will change it so that it will change its behavior. Neural network completely loses the physical significance, right? Kalman filter, given a set of data, it is a filter. First thing is a filter. It is not a model. We have to be very careful. It's a filter. Given a set of data, you can filter it out, right? And Kalman filter essentially assumes the system is represented by a model. Kalman filter doesn't assume. That is a different story. So Kalman filter can be used to filter out the data which is generated from nonlinear system. But Kalman filter itself is not a model. Kalman filter can do the very interesting jobs. In the image processing, signal processing, it is doing a great job. Give you an example here. V is equal to IR. Do you know the story behind that? V is equal to IR. Ohm's law, everybody knows it, right? When George Simon Ohm found this law, It is such a simple law. Voltage is equal to current to resistance, right? When you found this simple law, you can go and search in the web also. The people in that university, they just ridiculed him. He told, what the hell you are talking? The voltage is applied and current is produced and it is related by such a simple law. How it is possible? So he has to leave the university. 20 years he stayed outside. After 20 years, people realize that actually what he is telling is correct and these things. So we will talk about those things in the structure selection. You see, force is equal to mass into acceleration. You are, there is a mass, you are performing experiment. How do you know the force is related to acceleration or acceleration q or voltage q or displacement square or displacement exponential to the displacement? How do you know that? Now it is there that force is equal to mass into acceleration, you know it. But that is that term which is important. That is called the structure selection. So that is the most difficult part. So there is a system, there are different terms, which we will discuss those things later on. So Kalman filter essentially assumes, it is not a model. It assumes the system is described a model. But what we are going to say, no assumption. Given a set of input output data, what is that? Which term has to be there? Where acceleration will be there, displacement will be there, which term will be there? Very difficult problem. Very few people are working on the identification, very extremely difficult problem. Okay, and I will tell you many controversial things. So Hamilton model, Wiener model, they are used for biomedical signal processing. And if you have got some doubt, ask David West. David does it. I was working with him in Canada when I was there. And he works in some place in University of Delft. Few people are working. And we have got lots of ego problem actually. When you go, we are in Singapore conference, one of my friend in Brazil, I just close it before I will have a coffee break. The Leonard Leung is a big shot in Sweden, big shot in system identification. So there's some group, Leonard Leung was delivering keynote speech. There are 500 people there in the Hyatt. So there are some people sitting there other side. Somehow they could know it. I've got another two people from one in Malaysia and from Singapore. We are all working with Steve Billings. You will be surprised that, you know, Billings people, don't talk to them. Billings people, you see. We are working with Steve Billings. So, Edward told me, hey, Swai, you know, there are the bloody bastards, there are living people, they are not living people, they are talking now. Don't talk to these people, they are Billings people, you see. So, when you work with a very big source, when we give the theory and people follow it, then that's the problem. Then that's the problem. Right? So, I fully agree that the Kalman filter can do this, but Kalman filter is not a model. We'll see to that. So, nonlinear systems, we will see and we will have a coffee break. Only these three terms, the model should represent a wide class of systems. The model should be linear in parameters. Because if it is nonlinear parameters, you are in trouble. Okay. The parameters of the model should be interpretable, not like this neural network. If you can interpret a user should be able to extract, these things we will talk later, extract frequency domain information from the model, so that's it. We'll see. So unless these characteristics are there, we should not use the model, and we'll see in the next lecture how to fit the model. Gradually. Today you will do it, you will see.